Okay, so we know that rate of change is the negative 0.75 meters per second. And so then we worked hard in class. We said one of the most important things from class on Friday was, what is the fullest meaning of this rate of change? What's the fullest meaning? And so if you remember, we say, given any change in time in seconds, and so we were calling X was the time in seconds.
So I think we lost Mark for a second.
I'm here. I'm back. Can you hear me? Can you hear me?
We can hear.
Yes.
Yeah.
You can see my screen again? All right, so just be patient. I'll get back. When that happens, I'll get back as soon as I can. All right, so I need to. Okay. Oh, another announcement I wanted to make. You can, if you want to ask a question in the chat, every day one of the TAs will be monitoring the chat and answering your questions. So that's fine and good. Just be sure you don't get into too long of a conversation that you lose track of where I'm at, and then you kind of get lost because you missed a chunk of class. So yes, definitely, if you got a quick question, you can ask it in chat. Either Zach or Steve will be replying to you in the chat room, okay? All right, so we said that the rate of change is the negative 0.75 meters per second. And the fullest meaning is given any change in time, so given any change in time, the change in height of the flag can be calculated by taking that constant rate times whatever change in time you said. Okay, and this should make sense. How far does it go down in 10 seconds, right? In 10 seconds, you would multiply this by 10 to get how far the flag went down. How far does it go in 1/10 of a second? You'd multiply this by 1/10. So that's all this is saying. It's saying, given a change in time, you would multiply it by your constant rate, and that would give you how much the height changes. Okay, so where did this accumulation function come from? Where did it come from? Well, this was our constant rate. And we said we're going to start tracking changes at 0.6 seconds after the flag started coming down. So what is x minus 0.6? Well, that's just our dx. And net accumulation is amount of change, in this case, amount of change in height. So this function really just came from that equation, dy equals mdx, that we just mentioned here, which frames the meaning of that constant rate. Okay, so the independent variable of this is x. X is the time since we started lowering the flag. And then the dependent variable is a little more complicated. What's that? The change in height since 0.6 seconds, right? So it's a function of time since the flag started being lowering, time equals 0. But then the value gives you the change in height since 0.6 seconds after the flag started being lowered. Okay, so make sure you understand that the independent variable is the overall time, the time since the flag started being lowered, but then the value of the function gives how much the height changed since 0.6 seconds. And again, you can also interject questions. I'm still fine with that. If you just speak out verbally to interject a question, that's fine, or use chat. It's either way. Okay, so then I asked you to investigate the meanings of points. And so a really important thing about graphs is that when you look at a graph, you have to think about that red line It's not like a stick or even a line, but really it's a representation of many, many, many points. It just takes too long to draw it that way, right? This is like a zillion points along here. And because it's kind of clumsy and takes too long to draw them all or to show them that way, we just go fast and draw that. But then when you see a graph like that, you have to think, oh, that's just a mess of points, just a bunch of points. Each point has a specific meaning in terms of how the quantities are related. So we got is this 2 point, it looks like 2.3 seconds. So this is the point 2.3, negative 0.75, and it says that point represents the fact that at 2.3 seconds after we started lowering the flag, the rate of change, the rate of change graph, is the negative 0.75 meters per second. Okay, over here, this point, this is at 0.8. And what is that? Is that negative 0.15 meters? Do I have that Y value right? Okay, so what does that point say? That point says that, so again, so this is our net accumulation function starting from 0.6 seconds. It tracks the net change in height of the flag as time goes by. And so this point says that at, am I still here?
How did you get negative 0.15
So
to the Y value?
I might have done it wrong, but it's the Y value in our function when x is 0.8.
Oh, okay. I just looked at the Y and then counted. So I didn't
So you
plug it in.
just kind of estimated it visually?
Yeah.
Yeah.
Well,
so,
I just looked at 0.5 and then I counted. It looks like it's 0.7. That's why it was, because then 2 is the next value. But I didn't plug it in, so.
yeah, so we got the rule right here. Okay, very good. So what does this point on the graph mean? It means that at 0.8 seconds after we started lowering the flag, the change in height is negative 0.15 meters since 0.6 seconds. Okay, so that's how much change in height we got. Like shown like that vertical line right there represents that negative 0.15. It's how much the height has gone down since 0.6 seconds after we started lowering the flag. Okay, and the same thing here. This is just as this purple line represents a bunch of points. So that's how you have to see it. When you see a graph that's a line or a curve, you have to think, oh, those are points. Every point is a correspondence of two values of my quantities in question. Okay, so at 0.8 seconds, this is how much the flag went down. And that's what that point means. Okay, any questions on the homework?
Yes, what did you mean by after, so it's 0.8 seconds after the 0.6 seconds? Is that?
No, so the independent variable of this function is time since we started lowering the flag. So that's time since 0. So when x is 0.8, we're saying 0.8 seconds after we started lowering the flag at time 0. Okay,
yeah,
but then
sense.
when what the function gives then, this net accumulation function, is it gives how much the height has changed since 0.6 seconds, right? Because at point, in this net accumulation function, at 0.6 seconds, we have 0 change in height, and we're tracking change in height starting from 0.6 seconds. Does that clear it up?
Yes, so you said that you're starting to track the difference in height after 0.6 seconds.
That's what this function does. Because we have the x minus 0.6, our change in x is always starting from 0.6 seconds. So
Okay.
that's what the result of the function will give. But the independent variable is the time since we started lowering it. Right? So at 0.8 seconds, the amount of change, our dx so far, is 0.2 seconds. So in those 0.2 seconds, the height of the flag dropped this much. Does it make sense?
Yeah, that makes
Okay.
sense.
Awesome. All right, so let's, I just want to give you a, you're going to be working on the GC assignment. You're also going to have some time and a little bit of time in recitation to talk about GC, but I'll just do a brief intro of GC and we'll relate it to this example here. Okay, so GC window. Can you see the GC window here with the pink square?
Yes, we can.
Thank you. Okay, so in GC, you have math lines. Math lines have a colored square at the beginning. You also have text lines. If you do Control T, you get it's for your own notes and organization of your file. You can do text line. So to get a new text line, you do Control T. To get a math line, you do Control Return. So I have two math lines showing here, but nothing on them. So the first thing, GC is just a calculator. So I can do 5 times 67.2, and as long as I have a valid expression here, it's going to give me the result. Okay. So and then for pi. So you can highlight and hit divided. It's nice, it shows fractions in vertical form rather than having to do everything horizontally. For pi, just do pi. So here's 5 times 67.2 divided by pi. And then square, you can square a number by doing Shift 2. Just automatically gives you square. Shift 3 gives you a cube. That's too many exponents there. So notice there, it's not a valid expression, so nothing shows up here, right? So no answer shows up if it's not valid. It's waiting for something there. So I can.
For square root.
So then cube is Shift 3. Any other exponent, you do Shift 6, and then you type in your exponent. Okay. So and then you can highlight. You can cut, copy, and paste expressions. That's really convenient. Square root. So it's Control Shift R. And then if you're on a Mac, you could also use Option V. But Control Shift R works on both Windows and Mac. Option V works for Mac only, for square root. Okay, so that's calculations. And like I said, you can copy and paste. You can start a new line, and you can paste on a new line. Okay, was there a question?
How do you do roots that aren't squared? How do you do like cube roots, fourth roots?
So you'd have to make it an exponent, right? So if you want the fourth root, you do exponent 1/4.
Okay.
Yeah, there's not a built-in root that's not square root.
Well, thank you.
Maybe in the latest version there is, but there wasn't in the past. But you can always do the exponent with the fractional power. Okay, so then points. So let's graph some points here. To graph a point, you do Control 2. Okay, and so in Control 2, and so that point that we just had there was 0.8. So you can 0.8, and then tab will take you to y, and then negative 0.15. Oh, get it? Negative 0.15. So that's that will graph a point. So now when you have something that is graphable, as soon as you have something valid that's graphable, you'll see this graph button show up. And so hit graph. There's that point. I just plotted the point 0.8 to negative 0.15. Okay, and then we had our function. We had our net accumulation function. So let's do that. So if I do A, so when you define a function, you have those parentheses, right? You have those parentheses in function notation. For that, you don't want to do Shift 9 for those parentheses, or else it'll think it's multiplying. So if I do Shift 9, right now it's thinking, well, I'm going to multiply the value of A times what's in parentheses. That's not what I want. So for function notation, you want Control 9. This is super important. It's a big reason students, GC isn't working for them. it's because you have some kind of function notation and you didn't use Control 9, you used Shift 9. So I want to define my function a of x, negative 0.75 times x minus 0.6. Okay, now I'm going to graph. And so why did it not graph anything? Well, because that's the definition of a function, which the graph of which is just one representation, right? This is not telling GC to graph anything, but what it's telling GC is it's just defining this relationship between our dependent variable a of x, and the independent variable x. And so when I define a function, I can use any free symbol I want. So this is defining the exact same function as I just did. So it's going to look for this symbol in our rule, and that's what's going to plug in to calculate values of the dependent variable. So now I want to graph this. How do I graph this? To graph in GC, you're going to use x and y. Whenever you type x and y in a command line, GC will interpret that as, oh, you want to graph. So where do we want values of the dependent variable? So if we're going to do a conventional graph here, where do we want values of our dependent variable? X-axis or y-axis?
Y.
Y. So I want y to equal values of the dependent variable, a control. And so if I want to get fancy, you can use subscripts. So if I want to make it just like this one, I can do a control L, gives me subscript. And so I'll make it the a sub h. And then I'll do that here as well. So L, so a sub h. All right, and so then my dependent variable, which is in the parentheses, I want to show that on the x-axis, so I need to put an x there. I'll graph that blue. So now it shows up. But we only care about this function for values of x greater than 0.6 because this is the net accumulation starting from 0.6. So I can put a comma after my graphing line and say, oh, I'm just interested in x greater than 0.6, and it'll only graph it for those values. Now this is getting a little tight here. I want to zoom in on this. So down here in the lower left corner, you have to zoom out and zoom in. So I'm going to zoom in. And that's looking a lot more like the graph that I gave you. Okay, and you can zoom in on just the x-axis, just the y-axis, and you can see how to do that on your cheat sheet that I posted on modules. You can also click on the graph and get crosshairs, and then drag those crosshairs, and wherever you drag them to, then it'll pinpoint and tell you the coordinates. So right now, this is the point where we're at 1.6. Around 1.6 seconds since we started lowering the flag, and let's do another point. So here's 1.2875 seconds since we started lowering the flag, and the flag has come down about 0.51 meters since 0.6 seconds, right? Since 0.6 seconds. Okay, so that's just a few of the basic things that you will be doing a lot of. Plotting points, defining functions. And so say I want to actually plot this point for 1.28, so I could start a new math line and do Control 2. And it was, what, 1.2875? So how can I get an accurate value for the y coordinate that I want to plot here? Point black, say. What's my most efficient way to get an accurate y value or net change at this point in time?
You could plug it into the equation and solve for it.
Okay, yeah, so I could plug it in and solve for it, but I have actually a much more efficient way to do that.
Can you do a of, and then that x value?
Yeah, so
Like
this
a
is
subscript h.
This is going to be a huge theme in this course, is how powerful function notation is. So all I need to do is do the a sub h of 1.2875, and since that function's already defined, It will plot the point exactly on that line. That point is truly on the line because I use function notation and not approximation. Okay, any brief questions on GC?
In regards to plotting points, like with the last point that we just plotted,
Yeah.
do you have to click enter for it to plot or no?
Yeah, so if it's not graphing and you have the graph is highlighted blue, then you'll have to hit return or click on graph.
Thank
yes,
you.
whenever you change something or introduce something new to the graph, then you'll have to regraph. You'll have to hit enter. And you'll know, like if nothing's showing up, you know you're graphing things and nothing's showing up, then that might be just as simple as clicking on the graph button. Okay, so let's jump into new material. Got a lot to cover here and 15 minutes to do it, so here we go. Where am I? Up there. Oh, here we go. Okay. All right, so this is our endeavor right now. We are talking about, you know how fast the quantity is changing at every moment. You want to know how much of it you have at every moment. Okay, so the first principle was rate of change, and the second principle was an accumulation function, net accumulation function. So now let's talk about changing rate of change. So far we've really just only talked about constant rate of change. And so here is another version of the rate of change for lowering the flag, which is maybe a little bit more realistic if a soldier is doing this manually, okay? And so what's happening? So in general, it's coming down at negative 0.75 meters per second. But what would be happening here that it would kind of maybe slow down and pause for a moment and then head down again and slow down and pause and then head and slow down and pause. So why would that be more realistic? And so many of you are thinking this is when hands are when the soldier is changing hands, right? When the soldier changes hands, the flag is going to pause for a moment, and then when the soldier is actually pulling the rope down, that's where the constant rate occurs, and then change hands, and then pull, and then constant, and change hands, and then pull. So really, in life, you know, there are many things that are modeled pretty accurately by a constant rate of change, but many things, quantities change with a changing rate of change. Okay, so if we wanted to sketch that net accumulation function, starting from 0.6 seconds, we know it would be 0.6, and then instead of going down at a constant rate, now we have these kind of pauses, and so what will that look like? Something like that, right? So when hands are being changed, then we see like zero change in the height, and so the height's going to level off, and then it's going to head down when the hand is pulling, and then it's going to level off when hands are changing. So this. Okay, am I sharing my screen again?
Yes, you cut out for a minute or so there.
Okay. Was I talking about this graph?
Yes.
Okay, so this is now the more realistic net accumulation graph based on the more realistic changing rate of change function. Okay, so how fast this endeavor, how fast a quantity is changing every moment, you want to know how much of it you have. So how fast a quantity is changing every moment is our rate of change function. So in this problem, we're given the rate of change function. We want to know how much of it we have. Well, that relates to the net accumulation function, right? So net accumulation and how much we have are very closely related, right? If you know how much change you have, then it's pretty easy to figure out how much you have, okay? But how do we do this? How do we write a net accumulation function when the rate of change is changing? Okay, so this throws a big wrench in this developing the net accumulation function. If the rate of change is continually changing, then we can't just use dy equals mdx to get changes. Okay, so how do we do it? Okay, well actually we do want to leverage what we learned about dy equals mdx, because that's a very straightforward way to get changes dy. So here's that changing rate function. What we're going to do is we're going to split up the time into intervals of 0.35 seconds. And here's what we're going to do. We're going to build a net accumulation function based on constant rates in each interval. Okay, because we have the mathematics of constant rate, right? If we have a constant rate of change, we can use dy equals mdx to get a little bit of change, dy. And that's very straightforward and simple. So we're going to leverage that dy equals mdx. And so we're going to build a new rate function based on this one that's trying to be like this one, but is made up of constant rates. Okay, so in this first interval, starting at 0.6, interval of 0.35 seconds, the constant rate that we would pick would certainly be this negative 0.75, because all along there, the rate of change, according to the blue graph, is pretty much that 0.75. Okay, so what about in the next interval? So in the next interval, we need to come up with one constant rate that's trying to be like this very widely varying rate. So it starts at 0, goes up, or sorry, starts at negative 0.75, goes up to 0, and comes back down, all in that interval. But we just want one constant rate. So we want to kind of say, all right, what would be the best match? Well, it starts here, goes back up to 0, and back down. So something in the middle, right? Something in the middle. So I called it negative 0.4. So that negative 0.4 is the kind of like the best we can do with one rate of change to mimic this changing rate in that interval. Does that make sense? Okay, what about the next interval? Well, the next interval.
I have a question.
Yeah,
So I wanted to know how we reach negative 0.4. Are we?
This is estimate. We were all doing this. We'd all come up with something different.
I see. Okay.
But we all should be close to the halfway point.
I see. Okay.
Negative 0.3, negative 0.4, maybe negative 0.5, but it wouldn't be negative 0.1, and it wouldn't be negative 0.7, right? Somewhere in the middle. So what about this next one? Well, the next one, most of it is again at the negative 0.75. And what about this one? It spends a little bit of time down here at negative 0.75, and then we get all the values up to 0. So then is our kind of guesstimate, is it going to be lower or higher than the negative 0.4?
Lower.
A little bit lower. So I said, again, everyone would do something different. I said about negative 0.5 for this one. Okay? In this one, again, it takes all the values from 0 back down to our negative 0.75, but then has an even longer span here at negative 0.75. So I said even a little bit lower than that, negative 0.6. So what am I doing? I'm creating a new rate function from the old one that's trying to be like the old one, but it's made up of constant rates. Because with constant rates, then we can apply dy equals mdx and start working towards accumulation, dy. Okay, notice this one now is kind of the mirror image of this one.
Thank you.
This is the mirror image of this. So I said negative 0.6 again. And then this was kind of the mirror image of this one back here, right? So it has all the values from 0 to negative 0.75 and a little bit of negative 0.75. So it's much like that one there. So I said negative 0.5, and then the last interval, negative 0.75. So once again, the red function, I just created a new function. Oh, by the way, this was where the notes picked up, right? So if you have those note sheets, I gave you a chance to create that graph as I was creating it. So again, the red function, super important. We call this a pretend rate function. It's pretending to be the original changing rate function. Okay, and so Yeah, and how is it doing that? But it's doing its best to be the blue changing rate function, but with constant rates over fixed intervals of 0.35 seconds. Okay, so now we're going to make this table. And in this table, you see we have the time elapsed at the beginning of each of these intervals. So 0.6, 0.95, 1.3, etc. So these are intervals of 0.35 seconds. And we want to build towards accumulation here. We know how fast it's changing. That's our rate function. We want to know how much of it we have. So we're trying to get accumulation from this rate function. All right. So our approximate rates are the ones that we just did. So what did we say? So in the first interval from 0.6 to 0.95, we said that we're going to just estimate the rate as constant at negative 0.75. And then the next interval from 0.95 to 1.3, we estimated negative 0.4. And again, if we were all doing this separately, we all might have slightly different numbers for this. It's just an eyeball kind of technique. All right, and then in the next interval from 1.3 to 1.65, negative 0.75. Next interval, we said the rate was 0.5, etc. Oops, that's 5. And then negative 0.75. Okay, well now we have constant rate of change, right? Now we have constant rate, so we know what the approximate change in height is in each interval. How will we get the approximate change in height in that first interval from 0.6 to 0.95? What will we do? So the approximate change in height is dy. How do we calculate dy?
Engineer M.
Right, so here's our rate, here's our constant rate, m, times what's our dx? So our dx is the 0.35. So when you multiply the rate times the negative 0.75 times the change in x 0.35, you get negative 0.2625. And now in the next interval, it's the same dx, but it's at a slightly less negative rate. So we're going to apply this rate to get the change in y in this interval. So we're going to take negative 0.4 times dx, which will be the 0.35 again, and we get negative 0.14.
Wait, how are you getting 0.35 for the dx? Are you finding
Because it's every interval. So we spent the first 0.35 from 6 to 0.9 at this rate, or 9.5. And then starting at 0.95 to 1.3, we were at this rate, this constant rate. Does that answer it?
Yes, that answers. Thank you.
Sweet. Okay. And then in the next interval, we're at this, back down at this rate again. We multiply it by our change in x, and we get the same negative 0.2625. So we're just now the approximate change in height. We've got constant rate, so we can use mdx. Okay, negative 0.175, negative 0.21. Okay, so now, etc. Now we want to, what do we want? We wanted the net accumulation function, right? Principle 2, we want the net accumulation function. These are the individual changes in each interval. Now we want to build the net accumulation of height from the individual changes. So how much has the height changed since 0.6 when we're at 0.95? So now 0.95, that's a moment in time. How much has the height changed since 0.6 seconds?
0.35.
This one, right? This is how much it's changed, right? Now, when we get to 1.3 seconds, now how much has the height changed? What will we do? So we want the net change in height since 0.6. So it's going to be all the change in height we had before plus the new change in height, right? So it'll be, you add these together. We're going to add the negative 0.265 that we had in the first interval plus the new change in height in the new interval. So we get negative 0.4025 by adding this. So now our accumulation of change is this, and then when we let another 0.35 seconds go by, now how much is the net accumulation of height? It's going to be everything we had so far plus the new change. Is this making sense?
Yes.
Yes.
So what is it? Net accumulation is like a running total of changes. We're summing up the changes bit by bit, right? We're summing up the dy's. We have the first dy, and then by the time we get through 2 intervals, we have the total of the dy's in the first 2 intervals. And then when we get through 3 intervals, now we have the sum total from the changes from the first 3 intervals, etc. So we're going to keep making this progressive running total of changes in height, and then these 2 columns then form the net accumulation function. For this red pretend rate function. So this net accumulation function will be approximate because it's based on the red rate function, not the actual blue one. So it's approximate net accumulation function. And where do we get those values of net accumulation? By getting the dy's in each separate interval and then keeping track of the running total. Summing up the dy's interval by interval.
So the net accumulation is the changes within the changes, like how much.
It's the accumulation of changes, right? So at any given time, it's the sum of all the changes so far.
Oh, okay.
So the change here at this moment is going to be the sum of all these changes, because that's how much change we've had since 0.6 seconds.
And so that tells us overall within the problem how much the flag has gone down so far
At each time. But it's approximate because it's based on these constant rates. It's not the actual rate function, right?
Yeah.
So
it gives an approximation of how much the height has
changed at any time. Right. Just like just like the one we had before. But now we've broken it up into a bunch of little constant rates, and so we have to do it piece by piece. Instead of being able to do it all at once, we have to do it one chunk at a time and keep a running total of those chunks of changes. Okay, your quiz is open. 3 questions. I'll stay in the room for a bit. If you have questions, you can ask me, or you can chat with the TAs, but quiz is open. Go take it, and I will see you. Remember, all that your information about homework is on Canvas, and I'll see you on Wednesday.
Mark?
Yeah.
For number 2, what key concept allows computing the approximate change of height in each interval? Could you go over that really quickly?
Yeah, so that's this one here. So how do we calculate these changes in the 3rd column?
By doing m times dx.
M times dx.
Yep. Okay.
Yep.
Thank you.
You're welcome.
Is Principle 5 gonna be reviewed on Wednesday lecture?
Yeah, we didn't get to Principle 5.
Okay.
Oh, maybe we did. Let's see. Maybe we did. I just never said it. Let's see here. No, we didn't get to Principle 5. We only did number 3 and 4 today.
All right.
Or actually just, yeah, so Principle 3 was changing rate of change. Principle 4 was pretend rate function. So that's
okay. Perfect.
That's all we did. Yep.
Thank you, Professor Ashbrook.
You're welcome.
Can we see where like those red lines come from again? I'm just having trouble understanding that.
So we
How
were,
do we calculate those again?
yeah, so we were eyeballing, we were trying to come up with one rate that tried to be like all these changing rates. So for instance, do you see how the rate starts at negative 0.75 and goes up to 0 and then back to 0.75 in this interval?
Yeah.
Do you see that?
Mm-hmm.
So we've got a whole mess of rates, right? From negative 0.75 all the way to 0, back to 0.75. But what we want to do is we just want one constant rate that's trying to be like that. So would we make that constant rate up here? Would we make that like 0.1?
No.
No. Would we make it down here like 0.7?
Yeah.
But do you see how the rate was all these all these values up here? So it's kind of like these red lines were kind of like we're eyeballing an average.
Oh, I see that. Yeah.
So because it started here and went up to the top and then back down again, the average is going to be somewhere in the middle.
Okay, I see that. Thank you.
But like on this one, it had all the values here, but then it spent a good chunk of time down lower, right? So that's going to pull this average down. So that's why I picked a lower value for this one.
Okay.
Is that better?
Yeah, yeah. Thank you.
Sure.